If you're looking at just a line, then you're looking at only one dimension. The only thing you can do is go left or right. And that's fine, and we've done a lot of stuff in one dimension where you're just using a number line. If you put another number line on it and start measuring distance in a perpendicular direction this way, then now you're working with two dimensions. And that means you can go anywhere in here, right, because it's a two-dimensional plane. And if you put one more axis that's perpendicular to both of those two right here and give it some depth, now you've got three dimensions. We measure in one dimension using units, and the units can be anything. They can be inches, they can be miles, they can be centimeters. You can use anything as a unit. When you move into two dimensions, you're using the same kinds of units, but in two directions. And the two directions make squares. And you measure area in terms of squares. So if I go 1 unit this way, and 1 unit this way, and make right angles out of all of it, I have 1 unit square. And that's, whereas this is units, this is written as units squared, because essentially what you're doing is making a square out of your single unit so that you have something to measure with. And the same is true if you decide to go to a third dimension. You put a block there. As long as this is the same height as this is long and as this is long, then this becomes a unit cube. In order to measure distance, we use units. In order to measure area, we use units squared. And in order to measure volume, we use units cubed. You'll notice here that as long as I stick with something that's made out of squares, a rectangle or another square, it's very easy to count how many squares I have. I don't even need to count all of them. I can just count how many spaces I have at the top and how many spaces I have at the side and multiply those two numbers together. And when you're doing that, sometimes it's referred to as length times width. Sometimes you hear people call it base times height. And both of those are true. But when you're talking about base, you're actually talking about the segment that is a side of the shape. And when you're talking about height, it doesn't necessarily have to be a side in order to figure out what the height is. You get to see that if I make a parallelogram. If I make a parallelogram like this, the base is 2 units because I go 2 units, 1, 2. You measure the height, which is the perpendicular line, perpendicular to the base, to the point where it intersects the opposing side. And here, this is 2. Okay? If you look carefully, you'll see that I can take this parallelogram and cut it like this, take this part right here and move it over here and have a square. The square will have the same area as the parallelogram because I took some of the area from it and moved it to another place. Area is additive. Another way to put that, if I have a shape that looks like this, right, little house, if I want to know what the area of this is, I get the area of this rectangle, get the area of this triangle, add them together, and I have the area of the shape. Well, the same thing is true over here. If I get the area of this half of the parallelogram and the area of this half of the parallelogram and put them together, I still have the same area because I haven't expanded or shrunk the amount of space that I'm taking up. So in this case, we don't say length times width for a parallelogram. We still say base times height because we're finding a base, and from that base, we're measuring the height from the base to the highest point of the parallelogram. Triangles form an interesting situation. Let me just draw one here. It's got a base, and clearly it has a height. But the other thing about this is that if I took this triangle and reflected it and rotated it and put another version of it right here, I would have a parallelogram. And that's true of any triangle you can draw. You can get a parallelogram by reflecting and rotating and translating until finally, for this one, it's pretty straightforward. It would just be turned around like that, and you would have the parallelogram. But that means that a triangle is always half of a parallelogram. So I would get the area of this by finding the base and the height and multiplying them together. The area of a triangle is 1/2 of that. So going to our document for the first time, let's go ahead and label it area volume. And just to make sure that we've covered everything I just said, we've got length is measured in units, area is measured in square units, which is sometimes also written as units squared, and volume is measured in cube units, or sometimes written as units cubed. For a rectangle, a square, or a parallelogram, and keep in mind I'm listing them as being separate, but squares and rectangles are also parallelograms. For all of those, the area is equal to the base times the height. Now going back for a minute to my parallelogram over here, notice that I called this the base because I'm human and I have a predilection for using things as if there is an up and a down, as if there's gravity. But I could turn it this way just as easy and look at this length right here and call this my base and call this my height. There's no one right way to decide which angle is the base and which one is the height. So I can find the base here and the height would be here, or I can find the base over here and the height would be here, or I could find the base here and the height would be here. I can do this any way I want, but the bottom line of it is the area of a triangle is always 1/2 the base times the height. Okay. There's a shape called a trapezoid where you have two sides that are parallel, but the other two sides are not. Neither of these two formulas apply to this by themselves. But the thing about a trapezoid is that if you take a diagonal and draw it straight across from here to here, you are creating two different triangles. You've got this one and this one. They both have the same height from here to here, from here to here, from here to here. It doesn't matter where you measure it. The height of both triangles is the same, and it's the same as the height of the trapezoid. We have two different size bases, so let's call this one base 1 and we'll call this one base 2. Well, we can find the area of a trapezoid by finding the area of the two triangles and adding them together. 1/2 base 1 times the height plus 1/2 base 2 times the height. Using triangles and our ability to get their area, we know how to get the area of a trapezoid. So let's put that in here as well. This technique of cutting things into triangles and measuring the area of the triangles and then adding them up is actually very powerful, and we can use that in many ways. One way is when we're looking at polygons that are regular. A regular polygon is a polygon that has all sides equal and all angles equal. So regular doesn't just mean like plane. It's actually a special thing. It has congruent sides and congruent angles. If it's regular, then it means all of these are the same size. All of these are the same size. This angle right here. All of these angles are the same size. Just same. There are three kinds of angles that we talk about here. One of them is the interior angle of the polygon. One of them is the exterior angle of the polygon. And the third one is the central angle. For a polygon, you get the central angle by connecting the center with the vertices, with the end points of one of the sides. The thing about central angles is they always make a total circle. They always add up to 360 degrees, right? The sum of the central angles is 360 degrees. Well, that makes it fairly easy if I'm looking at something like this. This is 8 sides, 3, 4, 5, 6, 7, 8. And what I've said is I'm breaking this into congruent angles all the way around by connecting the vertices and the center. So I have broken this 360 into 8 different angles. That's how I can find the measure of this angle of one of these triangles. This angle right here is going to be 360 divided by how many sides there are. Okay. In this case, this angle right here would be 45 degrees. All right. So interior angles add up to something different depending on how many sides there are. Right? The interior angles, the sum of all of the interior angles of any polygon is equal to the number of sides minus 2 times 180 degrees. If you want to see it, this shape, which has 1, 2, 3, 4, 5, 6, 7 sides, has 1, 2, 3, 4, 5 triangles. n minus 2. And each triangle has 180 degrees in it. That's how you find the sum of the interior angles. If you have a regular polygon and all the side lengths and all the angles are equal, you can find the interior angle by calculating what the measure of the sum of the angles is, and then dividing by how many sides there are. So let's go put some of this over here. Central angles add up to 360 degrees. Interior angles of any polygon add up to the number of sides minus 2 times 180 degrees. And if you want to find one interior angle of a regular polygon, right, you find the sum of the interior angles and then divide by how many there are, because they're all equal size. The one I didn't mention is exterior angles. You get those by extending a side. The angle that forms with a side and the exterior extension of another side, that's called an exterior angle. They also always add up to 360 degrees. If we take all of this and what we know about the area of a triangle, we can actually figure out the area of a shape like this. This is a pentagon. This is a regular pentagon. It has 1, 2, 3, 4, 5 sides. They're all the same length. They all have the same angles, which means all of these angles are congruent. I drew an extra line here to show you what this is called. This is called the apothem. It is also the height of this triangle right here. These are called radii, the lines that go from the center to the vertex. Those are called radii, or the singular is radius. But I can figure out what this angle is because I have 1, 2, 3, 4, 5 of them. They have to add up to 360 degrees. So 360 divided by 5 is equal to 72. This angle right here is 72 degrees. Now, whether I'm given the length of the side, or the length of the radius, or the length of the apothem, having one side and the measure of one angle creates a trig problem that I can use to find all the other measurements. Now, before we get too far, you got to look at it and say, wait a minute, I don't see a right triangle anywhere. Well, the right triangle is here because that's what a height is, that's what the apothem is. This has to be a right angle for this to really be the height, which means we're cutting this angle in half, so this is now 36 degrees. And using the sine, cosine, or tangent of 36 degrees, depending on which piece of information I have, I can find the base and the height, and when I do that, I can find the area of this triangle right here, and when I do that, I know I have 5 of them that are the same size that go together to make this pentagon. Going back to this for a minute, to get the area of a regular polygon, get the area of one internal triangle and multiply by how many triangles there are. Let me give you an example of this to work on. Let's take an octagon, and let's just pretend that that's a regular octagon, that all of the sides are equal, all of the angles are equal. I have 1, 2, 3, 4, 5, 6, 7, 8 sides. To get one central angle, I'm going to have to take 360 degrees and divide it by 8. And that equals 45 degrees. And let's say that this base here, the side length of my octagon, is 14 millimeters. If I break that triangle out and actually redraw it over here and say this is 45 degrees, this is 14 millimeters. And these are congruent because they're both radii of the shape. This means that I can cut this in half right here. Make a right triangle and have something else to work with in order to get the height. This new triangle that I'm working with now looks like this. Right, we split this in half as well. So now this is 7 millimeters. This is 22.5 degrees. And this I don't know. But this is a trig problem. Specifically, if I take the tangent of 22.5 degrees, that's going to be equal to 7 over the height of the triangle. This is exactly the same kind of problem you had to do in the last standard, and this is what builds on that. This is why you learn how to do that. So we know from doing this before that h is going to be equal to 7 divided by the tangent of 22.5. Now I can turn that into a number right away, but that doesn't necessarily help me. Because remember, what I'm trying to find is the area of this regular polygon to start with. So in order to find the area of this triangle, I need 1/2 times the base, which is 14, times the height, which is 7, divided by the tangent of 22.5 degrees. And I have 5 of these triangles, so I'm going to multiply that by 5. When I do all of this arithmetic, that is going to give me the area of the octagon. Actually, there are 8 sides. It's an octagon. Pentagon was the first thing we did. This one's an octagon. There are 8 sides. So 8 times 1/2 is 4, times 14, times 7, divided by the tangent of 22.5 degrees. This is something that you can do with a calculator quickly and easily. So let's do it. It's 4 times 14 times 7 divided by the tangent of 22.5 degrees is equal to 946.4 millimeters squared. What is it that this number is supposed to represent? Do you remember? Yeah, the whole thing. So that's what all of this is for. And then that's the area part. Volume, when you move on to the next dimension, actually depends on area. If you think about it in terms of just building something, if I have a floor, like the floor of this room, and it has square tiles, like the floor of this room, if I called the side of the tile here 1 unit, each one of these squares would be 1 unit squared. And if I put one block, one cube, one unit cube on top of it, in this case, I could fit as many cubes as there are squares. And then if I put another one on top of this, like this, now I've got twice as many cubes as I had squares. Remember that the number of squares is the area of the base And if I multiply that by the height of the 3D shape, right? Multiply those together, that gives me the volume of the 3D shape. So let me write that over here. That's called a prism. Prism has polygon bases that are parallel and congruent. And then for sides along the outside, the sides are made up of rectangles or parallelograms, one for each side of the base. The volume of a prism is equal to the area of the base times the height of the 3D shape. Now, I keep saying height of the 3D shape because I don't want you to get confused by the base of the two-dimensional shape here. You're not multiplying by the base here. You're multiplying the area of the whole base. And you're multiplying by the height, not the height of this square, but the height of the shape. Another quick extension of this. If you have a cylinder, it's not really a prism. Prisms can be with a triangle as a base. They can be with a square as a base. They could be with a pentagon as a base. But if you have a cylinder, the circle is not a polygon. So this is not a prism, but it's called a cylinder. And maybe not surprisingly, the same thing is true of this as it is for these. The volume of a cylinder is equal to the area of the base times the height of the cylinder. And since we're dealing with circles now suddenly, it's important to point out that a circle, the area of a circle, this is the radius here, this is equal to pi r squared units squared. Okay. The distance all the way around, which is called the circumference, of a circle, is equal to pi times 2r. In other words, the diameter. But that is all you need to find the volume of a prism or the volume of a cylinder. You need to be able to find the area of the base and then multiply it by the height. Another shape that we looked at is the pyramid. This has a pentagon for a base, and then the sides are triangles that meet at a point. Every pyramid is carved out of some kind of a prism. Let's see if I can make it a little more clear with something like this. The idea here is that if you started out with a block of wood that was a prism, and then you started whittling away, taking away the part that isn't part of the pyramid, you would wind up taking away 2/3 of the block. Most of the block would be gone. You'd be left with 1/3 of the block you started out with. And that's why if I try to get the volume of a pyramid, the volume of a pyramid is 1/3 of the area of the base times the height of the pyramid. And the same thing is true with a cylinder. If I took a cylinder like this, put a dot at the center of the circle up here and started whittling away, ultimately this stuff would all fall away. I would wind up with a cone, and the volume of a cone is equal to 1/3 the area of the base times the height of the cone. It's 1/3 of these up here. A couple of quick more things, and that is, if I have a circle, the area is pi r squared. If I want the area of a portion of this, it's called the area of a sector. And what I do is I take that central angle, let's just call it P for the proportion, the part of the circle. How much of a part of that is it from the whole circle? So it's pi r squared times the angle measurement of the sector divided by 360. What does that look like? Looks like this. If I know this is 5, then I know the area of this circle is 25 pi units squared. If I say I want 70 degrees, okay, then what I'm doing is taking this and multiplying it by the proportion of the circle that I'm taking away and measuring. 70 over 360, and then when you do that arithmetic, whatever that is gives you the area of the sector. And the same thing is true with circumference. If I know that this is 5, I know that the circumference is equal to 10 times pi. But if I want to know the length from here to here, then I have to measure the central angle that creates that arc, and whatever that measurement is, call it theta, we divide that by 360 degrees. That tells us the proportion of the whole circumference we're getting, depending on what angle that is. We multiply that by the whole circumference, and we get the answer. Okay, so I'm going to put that here too. And then finally, in this little bit of extra room here, a sphere. If I want the volume of a sphere, it equals 4 over 3 times the radius cubed times pi, and that's units cubed.